Is everyone able to see my screen?
Yes.
Okay, Yui, can I start?
Sure.
Okay, yeah. So today I will be presenting about a new topic. It's Pinecone, and it's being like nowadays it's growing so much popular. It's like a lot of like the company who developed this app is just earning in millions and billions because of it. And yeah, it's like very useful, especially if you have like a very large data and and you are working with it, and it's very difficult in order to store it and retrieve it. So in that case, it's very useful. It's just a like a vector database, which is like used for indexing and storing your high dimensional your data, which is to something like in the form of vectors. And with that, and the benefit of storing your vectors in the form, and benefit of storing your data in vectors is like it's we can perform the operations which we usually perform with vectors in here. Like you can perform operations like you can search with similarity, or you can transform many operations other than that, like how is any vector similar to another vector, or how much it's different. We can find out with this app very easily, as compared to like if we go without it. And if you're working with a very large data, it will take a lot of time. So that's why people thought of like storing their data in the form of vectors. And yeah, so it's like we have like huge amount of data. It's like just a second. So it's like we have data in the form of like a written document, or it can be in the form of post, it can be in the form of pictures. So we have like different types of data. And when we are when we are trying to find something, like we need to find any image or any type of document, when we are doing a Google search, then we need to modify our search based on the data, or based on what we want. We use like tags or terms. We add that in order to like refine our search. But if we store our data in the form of vectors, it becomes like very easily, we don't need such type of like modification in our data, and it can easily uh, be able to search for similar data or similar stuff what we are looking for. So it's all that, like these all data are unstructured, and vector data is a form of like representing these data in the form of numbers, so that the machine can understand it, and it can help you find similar data, yeah, based on what you feed as or your data in the form of vectors. So apart from that, what Pinecone does is, it's like it converts this unstructured data into what is called the vector embeddings. This vector embeddings is just like numerical representation of your data. It's just like storing your data, and it's doing the vector embeddings and thus storing it into the vector database. And so that this helps in like in fast retrieval, and as well as similarity searching. Both these functions, it plays a like a major function, because it this when you store your data in the form of vector, it becomes like this searching for similarity, or like fast retrieval of your data, it becomes very fast, as compared to like if you are working with normal data which is not converted into vector. So how it does converts it into this vector embeddings, it uses like a machine learning model which does these convertings into uh, yeah, in the form of numbers. And for example, it can convert anything into in the form of numbers, like in a person's name, any object, or any data you feed, like a word or a sentence or an image. It can convert it into like in the form of vector database. These colored small balls, it's like I made it manually, but it all represent like these are the similar vector database components, and which it's storing the data. And this is the same model, the Pinecone, which is doing this. Yeah, I wanted to illustrate this concept through this diagram. And After embedding, it stores this into the vector database, and this vector database helps to find out the query result. It's like uh, whatever question you ask, based upon the vector database's understanding, based upon the model's understanding, it finds out like which would be the most appropriate answer to your query. So this diagram is like illustrating that. So apart from this, it's like indexing of these vectors, which we are storing as data, which we are storing our data, is very important, because it helps in like your search or your retrieval becomes very fast because of this indexing. It's like numbers in the form of, like, you can see the numbers here. So the machine is able to understand that number more easily as compared to like if it's in the form of a text or an image. And since it can understand it very easily, so that's why it is able to perform the operations based on that. And so it's like, mostly when we think of dimensions, like as humans, we can think of like maximum of 3 dimensions, or yeah, but like only 3 dimensions. But because human brains are like working, like they don't go beyond 3 dimension, but there are more than 3 dimensions, like there are 4 dimension and 5 dimension. So Pinecone is designed to work in like hundreds of dimensions. It's like I mean, we can't visualize it, but it can work in that environment and with that dimension. And it also, with converting the data into vector form, it does that. It helps in similarity, in searching for similarity of vectors, or performing any operations on vectors. Apart from that, it can also it does that by calculating distances, or by like doing the neighbors, or by searching through the nearest neighbors. And based on the distance, it can find out like how much one vector is similar to another. So indexing is like really important component of a vector database. After that, I also wanted to highlight that, um, just a second, yeah. So it indexing also maps the vectors to a new data structure, so that it will help in faster searching, and also it will enable more efficient search. It's like, since it's stored in the form of numbers, so it can be easily retrieved, it can be easily searched for like similarity. So these are the facilities which are provided by like vector indexing. And we can use vector databases to equip large language models like ChatGPT 3, 4, with long-term memory, which can help in like building like more advanced applications. And if in the implementation using like LangChain, which is now like very very popular, and it's being used like, because it provides such a framework in order to implement such large operations. So providing those applications with such a long-term memory can also help in like building a large language model application. Then so it's like, mostly it's based upon like your search, and it also like understands online, like online retailers, what they purchase, and whatever you purchase from them, it's based on that, like whatever you are purchasing, based on that they give recommendations. So Pinecone or other semantic search applications like that, they are also used in that form of applications. Next, I wanted to talk about the that the we are storing our data in the form of vectors. So there are two types of vectors. First is the sparse vector, and the other is the dense vector. Sparse vector is like, they are very limited, like you can see like they have a large gap between each numbers, so they are very less in numbers. So in that, data would be like stored in less quantity as compared to your dense vector, which you can see like there are more subdivisions here as compared to this. So it would be able to store more data as compared to this data. Apart from that, dense vector also has this advantage that it is used for comparison when we are comparing based on semantic meaning, I mean semantic search, because in that search we are focusing on the meaning as compared to like sparse vectors, which is good for like doing the search based on your syntax or this word. It's like, for example, if you have the words with a boy and a dolphin, or a boy and a giraffe, like a boy is going towards a giraffe and a giraffe is going towards a boy. It's like these there are like same words in both the sentences. If you would compare these two sentences with like the sparse vectors, it would be like difficult for it to understand that these two words are not the same, since it can find the same type of words in both the sentences. But actually these sentences are not the same, and dense vector helps in understanding those, because it does its search based on semantic meaning, and therefore it's able to differentiate them as compared to sparse vectors. So in that kind of search, dense vector searching is more efficient as compared to like sparse vector searching. And I also wanted to highlight, like as I told, like there could be hundred and thousands of dimensions, and what Pinecone does is it searches for the similar vectors and it clusters them together. It's like we can see in this picture, it's just like 3-dimensional image as we can imagine. So there are a lot of like vectors we can see here, but only these vectors, these are like the there is a sort of similarity between these vectors, like there are weekdays, there could be month, or there could be any other things which are very closely related. So what Pinecone does is like it clusters these type of vectors together, so that when you are searching for a vector similarity, it would be able to like provide that these vectors are more similar as compared to uh, other vectors, and due to that your search becomes more efficient as compared to like if you search it like without using this application. And apart from that, I also wanted to highlight one thing, that there could be about like sparse vectors and dense vectors, that um, even if there could be like uh, same meanings, I mean same, there could be different words which have the same meaning, then also sparse vector can say that these words are not the same, like good morning, or if we say like hello, hi, and like that type of words, these are like hello, hi, or there could be many other ways of saying that in different languages. So sparse vector would sense that it would different, and it would say like, yeah, it's different, but and actually it's not different. So in that case also, like the dense vectors is more appropriate as compared to sparse vectors. Then we also like when we were learning high vectors in high school, we used to perform addition, subtraction on vectors. So I wanted to highlight that we also use that property of vectors here. It's like we have like a data frame, we can and we have some sort of data in that. So in order to form like an operation like addition and subtraction, we can also perform it on the vector. It's like on the vector king, we minus vector man but add vector woman, then we can get something close to vector queen. So it's very cool, like when you can perform these type of operations in like such a large data, and it can be done efficiently. So it's like a great asset. Okay. And so mainly for Pinecone, we use dense vector representation because of these reasons. And we actually visualize these relationships in the form of vectors, and like mostly in the form of representation, we do like in the form of dense vectors. And most and these dense vectors could be represented for any type of data. It's like words, sentences, images, and any sort of dimension. It's not just three-dimensional, or just or 2D, which we can think about. It's like 700 to 800 or something like that. And apart from that, one of the earliest example which implemented this kind of technology in it was the word to vec, which we can understand like from the name. It's less just like it would convert your word, or it would store your word in the form of like vectors. So for word to vec, it's like uh, it analyzes the word for which we are making the dense vector representation based upon based upon two approaches. It's like first is based on like skip ground method, which is represented here. We are using the surrounding words and doing a one hot encoding. So the left side we have the sparse vector fox, and based upon the one hot encoding on the right side of the surrounding words, we get a dense vector representation of fox. And every time whenever in the text it will find fox, it will perform this operation. So one way of doing it, it's like that. And it mostly uses a neural network. It uses through neural network, and it compresses it, and during that stage the dense vector representation of a word is made. So mainly you are optimizing a neural network for this kind of vector representation. And for like similar to, it can be also like the second approach is, it can be also done in the form of like the, if there is one hot encoding on the surrounding words before and on the left hand side, and then it results in the sparse vector representation, and it's converting the sparse vector representation of the fox into dense vector representation. That is the other type of word to vec type of method, which is termed as bag of words, yeah, so collection of bag of words. So it's mostly the same. It's yeah, just swiping of the sides. So it's like that. And so it, because I think word to vec was introduced in around 2008 or something. So also, there are also newer versions of like we are converting sentence to vector or paragraph to vector. So we are using that technology for other, building upon that. And but for sentence like sentence to vector, we use a token by token embedding as compared to like word to vector embedding. Yeah, just I will show it through an code. So here we are like importing installing our sentence transformers package, and then doing the and then we imported the model this from mpnet base v2 from the Hugging Face co, and Hugging Face.co model. We have that Hugging Face library, and from there we downloaded this model and installing these libraries. After that we have got like a sentence, I mean a bunch of sentences. So here we are checking like how could the machine identify which sentence is most similar as compared to other sentences. So here we are first doing the encoding of those sentences, like here we are embedding it. We got like 7 vectors, which has like 760, each vector is of like 768 dimensions. And now we are doing like a cos sim function. It is used for like comparing the similarity. It's like it's the heart of Pinecone when you're using for similarity searching. It's the most efficient one. And for here also, like we are using the cos similarity function in order to find the like embeddings. We did embedding for the last sentence. The -1 represent this last sentence with the other sentences in order to find like which is the most similar. And then we are also calculating the scores so that we can find like which score, because whichever had the highest similarity would have the highest score. So from this we found out like this one, the fourth one has the highest score. So it's quite evident that it would be most similar to that. Then with argmax function, we find it like, yeah, which would be if from that output we can understand what if we want the machine to tell us directly the output. So here it does tell the output that, yeah, that sentence is the most similar as compared to that. Yeah, it's the same thing. It's like it's showing with each sentence, it's showing the similarity score, and then we are comparing it with the last sentence, which is showing here. Apart from this sentence similarity,
那个我这个就是我这个情况的话，就是出院以后啊，我大概多长时间？待会儿要给你。
Excuse me.
好，那我就算我还洗鼻子没有？
Could you mute your?
好。
Hi, Jing Dong. Could you mute yourself? Yeah, thank you.
他等会儿要给我讲出院的事项。
Oh, thank you.
我口号。
Mute him. Let me try. Okay, done.
so apart from that similarity search, we can also like do question answering with this, since both of these have the same concept of like comparing one with another. Like you are comparing based upon like if you are comparing similarity, or what if machine thinks is the right answer to your question. Both of these things, you are employing machine's ability to think in order to like what is more similar and what is the right answer based upon like the probability or the similarity score. So we also use like we also use it for question answering. In this, you import your question to a DPR retriever, and from here the question goes to the index database. After that, in this DPR, there is encoding of both the question and the context, and from that it goes to a reader. Like here, it's using the BERT question answer reader, but there can be other models also for like reading the question and the context, and based upon the Pinecone's ability, it understands like what could be the answer of your question. It could be like wrong, it could be right. So it's totally based upon that, and and on that it produces your results. So in this diagram, we can see like there's a question encoder and there's a context encoder, and both of them like encodes the question and the context, and both of these encoding is done in the same space, and with the optimization of the on the constricted loss function, so that there's minimum differences between the vectors, so that we can easily assess which vectors do have like similarities, since the vectors which would be most similar would have the least difference. So it's very important in order to minimize the vector differences in order to find that which vectors are similar. After that, like in the similarity search, it's also like doing the similarity, like the question and the context, which would be according to it's the most appropriate answer to that question based on the context, because context would be like it would have a single answer of that question, or it could have like multiple answers regarding that question. So it's we are employing the machine's ability in order to understand like what could be the answer in their opinion based upon their intelligence. So so this is the benefit of like training both the question encoding and context encoding in the same vector space. Apart from that, it's then fed into like minimizing the differences. Then we can see that through also like in the code form. Here you are like downloading the transformers from the Hugging Face library, and importing the DPR, that DPR retriever. Both the encoder, the question and the context encoder, and the tokenizers are there. The tokenizer mainly converts like your question into like numeric form, so that machine is even better able to understand it and process it. And then we are like initializing both of them with our questions. It's like, yeah, we downloaded all the packages, then we got questions like this 3 questions, and we are going to compare it with the context, and based upon that we initialized our models with that question and the context. So here it formed like, since I had like 3 questions, so there were 3 vectors with dimensions of 768, and the context also we had like 9 statements with each with 9 statements, so it formed 9 vectors with dimensions of like 768. And then we made a loop in the form of like going through each question and then forming the probability, like which question has the maximum probability with the context, and then it's gonna like compare it and show your answer. So in this, like I wanted to highlight in this example, since here I have put like the question in the question also as well as in the context also, in order to see like, is it like functioning like a sentence similarity, or it's functioning like finding out the answer based on its understanding about its intelligence. So I included one, there's also included a question in it. So it does answers the question. So it does shows that it's using its own intelligence as compared to like just seeing the similarity. But for, yeah, it's like for 2 questions it's showing the answers, the right answers, but for another question it's like it's not able to find the right answer. So we can't totally we can't, like, it's not perfect, it still needs more training in order to learn the, yeah, how it's a function and how to answer the right answer. So yeah, it's like one limitation of this model. And okay, another application is like which is, I think, yeah, my favorite is we can use image text embedding. It's like you can take an image, you can take a text, and then it would compare, it would do the same function. It's encoding both the text as well as the images in the same vector space, and it's matching at the, it's mapping them both at the same point in the vector space in order to find like, is that text related to that image in any form, like is it describing it, or it's like in any form it's related to that image. So it's also similar to like the sentence transformer or the question like the uh, question answering. Yeah, so in the same form it's doing the same in the same vector space, it's mapping through that DPR retrieval model. And based upon that, since here we have like 3 examples of pictures, we have like 3 dog pictures, a dog is running and it's hiding, and 2 dogs running. So we are going to test like, is this machine a model able to find the differences between the images, and also if it's able to find that this text is related to, which text is related to which image. So it's like we are going to encode both the images as well as the text, and then we are going to see like which is comparing, and then which has the most similarity with which image. We are going to see this. So here we are using like the image and text both in order to see the similarity between the two. So till now we were using like just the language part of the transformers model, or just using the language part, that just language, the similar sentences or question answering. But here we are also using images in order to like see if it's working or not. So I think that's very cool feature. So it's when we looked at the code for it, we yeah, installed our all library, and we installed this PIL for making our image object. Then we did this request for getting the images from the URL, and then we plotted it. So we got all these 3 images. As you can see that whatever images there was stored, they all, like, we can have those 3 images. Then we use like clip processor and clip model, which is also like a tokenizer. And this is the clip model is the thing which contains which is doing the encoding part, the encoding the text also as well as the image. So this clip bit is the visual image transformer, and it's encoding both of them in the same vector space and mapping both of them in order to see like they are related or not. So for example, we are taking like a captions, and we took like 6 captions. Out of them, only 3 are related to the image and 3 are just for tricking the machine. So here we fed all our input into the processor, and after that, when we asked to find the probability, we got like those 3, the first 3, the machine was able to find out that yeah, the first 3 was the image about, they are the like related to the image. And with that, with argmax also we got the same answer. So just to confirm, like yeah, so the machine like model was more accurate, was very accurate in terms of like image text embedding. And not only that, if even if you don't give like or like yeah, even if yeah, and here also like it's doing the same, like for 6 caption it's doing 6 vectors with 512 dimensions, and for 3 questions it's making 3 vectors with 512 dimension. And if even if you feed the just the caption, like here you have here there was only fed the caption part. I use the first caption in order to find like, is the model able to retrieve the image related to that caption. So I use the first caption, and it was and I used the similar cosine function, and it returned the similarity scores for that. And after that, it also was able to predict the give the output as the image which was the most similar for that. So yeah, it was like pretty accurate for this function. And lastly, I wanted to highlight about like, yeah, it's very useful. It's very easy to make a lot of like applications, but it does also have implications. So we need to like work on that. It has like maximum vector dimensionality of 20,000, and like maximum size of an absurd around 2 MB, or recommended absurd is just 100 vectors per request. And also like sparse vectors, you can't have like more than 1,000 non-zero values, and delete request is just 1,000. So we should be building in order to like increasing our capacity for these functions. Yeah.
Yeah, okay, thank you very much. If you have any question, feel free to unmute yourself and ask Sham Heavy. Okay, I have just one question, but it's okay if you don't know it. Do you know any other vector database, vector dataverse?
Yeah, it's like, are you like asking for any other options apart from Pinecone, right?
Yeah, and
Yeah.
their strengths and weakness.
It's like, yeah, it has like, I read about like 6 other type of vector databases. It was like Vespa, Chroma, and there was one more I remember. I didn't remember the name, but yeah, they are also like and they are also like Pinecone, but yeah, they do also have like limitations like Pinecone. So yeah, we need to like have more advanced technology for yeah, overcoming these limitations.
Okay, if you don't have any other question or comments, I will stop recording and end this meeting.